Hello and welcome back to another video. In the previous video, we had a crash course on kinematics. This video is all about dynamics for AS level physics. Now this is a crash course, so obviously it cannot include every single thing in detail, but I have included all the main concepts, including some examples and formulas that you need to know. If there is anything else that should be considered in this video, please let me know that in the comment. If you have any question or doubt, don't hesitate to ask in the comment section down below. Let's begin. Alright, let's start by reviewing the differences between mass and weight. Remember, the equation that relates both of them is W equals to mg, weight equals to mass times gravitational field strength. Mass is a scalar quantity. It does not represent direction, whereas a weight is a vector quantity. It has both magnitude as well as direction. The SI unit for mass is kilogram, the SI unit for weight is Newton. If you want to define them, you can say this. Mass is basically the property of an object that resists changes in motion. For example, if you compare a huge bus and a small bicycle, and somebody comes in front of them, you can imagine it's much easier to stop that bicycle compared to that bus, right? Because this bus has much bigger mass, much greater mass, so it resists changes in motion. Whereas weight is basically the gravitational pull on an object. Weight changes, so the weight on moon is going to be different than the weight on earth, but mass is always constant. Okay, let's look at this example. These are two different planets. The mass is same on both of them, but as you can see, the weight has changed. Why? Because gravitational field strength is different. On earth it's 9.81 meter per second square, but on moon it's 1/6 to that of earth. That's why you can see that the weight has reduced as well. A lot of people use these interchangeably, but it's not the same. This can also be found out by this equation where mass equals to force over acceleration. We will learn how this equation is derived in a moment. And remember, 9.81 meter per second square represents gravitational field strength. Another unit for gravitational field strength is Newton per kilogram. Now, before moving on to the three laws of Newton, let's review momentum because we will explore this concept in one of the laws. So remember, momentum is basically the quantity of motion. It is represented by the mass of an object and the velocity. If an object has a higher mass as well as higher velocity, it will have a really high momentum. A stationary object has zero momentum. The SI unit for a momentum is kilogram meter per second, but it can also be represented as Newton second. Why Newton second? You will know this when we derive it in one of the equation, and it will be clear why. Momentum is a vector quantity because it's a product of a scalar and a vector quantity. For example, in this question, if you're asked to find momentum, momentum is going to be 10 kilograms multiplied by 0 meter per second. So this is zero momentum. If an object is stationary, it has no momentum. Now, sometimes it's a good idea to know this conversion because some questions can be the values could be given in tons. So 1 ton equals to 1,000 kilograms. Okay, now let's move on to the laws of Newton. Now, Newton's first law states that an object will remain at rest or move with constant velocity unless acted on by external force. Now, let's try to understand this. The first step is clear, right? An object will remain at rest. If a box is resting on the floor, it will obviously not move by its own, unless an external force is applied on it, right? Unless you apply some force. That is clear. But what about that it will move with constant velocity and that it will continue moving with constant velocity? That does not make sense, right? If there's a ball and you kick that ball, it will move and eventually it will come to a stop. Now the thing is, you will think that it stops on its own, but that's not true. There's an external force acting on it, and that is called the frictional force. Frictional force in air is called as air resistance. In water is known as viscous force or drag force. Now this frictional force varies. In smooth surfaces, the frictional force is very, very low. That's why it's so slippery and it's much harder to stop. But in rough surfaces, for example on roads, the frictional force is a lot. Basically, frictional force is the force that is going to stop the movement. Is going to reduce and eventually stop the movement. But you can experience this object moves with constant velocity in space, because there are no forces, no frictional force in air in space. So if an object, for example a star or a moving object, is traveling in space, it will continue moving for eternity unless, for example, it interacts with another planet or some other object. Okay, hope that's clear. Now, when we talk about constant velocity, that means, for example, if the speed is 20 meter per second, it will remain as 20 meter per second. That means the acceleration is zero. It's not accelerating, the speed is not increasing, it's not decelerating, the speed is not decreasing as well. Now, whenever acceleration is zero, resultant force is also zero. Also important to notice that acceleration and resultant force are in the same direction. If resultant force is towards the right, the object will also accelerate towards right. Okay, now let's talk about resultant force. If there is an object, if this is a box, two forces are acting on it, okay, in opposite direction. This is 20 Newton, this is 5 Newton. Can you find the resultant force? The resultant force is going to be 20 minus 5, 15 Newton, because they're in opposite direction. Now let's imagine if both of these forces are in the same direction. If this is 30 Newton, this is 10 Newton. Then in this case, the resultant force is going to be 30 plus 10, 40 newtons, because they are both in the same direction. So you have to add it. Now, if we say that a car is moving, this is your car, the driving force is, for example, 200 Newton. And the frictional force, which is acting in the opposite direction, is 18 Newtons. So to find the resultant force, you have to subtract 200 minus 18 Newton. Now, if an object is moving at constant speed, that means constant velocity, acceleration is zero. The pushing force, whether it's by engine or it's by a person, the pushing force and the frictional force are both equal. Okay, resultant force at that situation is 0 newtons. And in this point, when the pushing force as well as the frictional force are equal and opposite, of course, because frictional force is always opposite to the direction of motion, acceleration is 0 and resultant force is 0 as well. Now we can also define inertia. Inertia is basically the property of an object to stay at rest or at constant velocity. If an object have a bigger mass, it has bigger inertia, and it's harder to start it from rest or break it or move it, okay, from its constant velocity. Just like a bus, a huge bus has much bigger inertia than a small bicycle. Okay, for a single particle, Newton's first law can also be described in terms of momentum. So you'll say momentum of a particle remains constant unless acted on by external force. Remember, Newton's first law says that every object continues in a state of rest or with uniform velocity unless acted on by resultant force, right? Let's say if an object is resting, what is the change in momentum? So change in momentum is mv minus mu. So this is going to be 0 because final velocity is 0, initial velocity is 0. It's at rest. So there is no change in momentum. The momentum is constant if there is no external force. Even if this was at moving, let's say at 30 meter per second, there's no final velocity and initial velocity would be same. So the momentum is constant if there is no external force. Now, Newton's first law explains when there is no external force, when there is no acceleration. Okay. Now, what about when there is a resultant force? When there is a acceleration, basically a resultant force is acting on an object. So there are two, Newton's second law is defined in two ways. The first one talks about momentum, and the second one talks about this equation, F equals to ma. Now first one, here we'll say resultant force acting on an object. Now we're talking about the resultant force. This will cause a change in momentum in the direction of force. Okay, rate of change of momentum is proportional to the magnitude of force. So here you can say force is directly proportional to rate of change of momentum. How does momentum change with time, which is said here in the second sentence. Now we can write this as force equals to momentum over change in momentum over time. Now whenever you want to remove this sign of proportionality, you need to include the unit or proportionality, but here it is 1. We'll write 1. So force is a rate of change of momentum. There is a resultant force happening, so there is acceleration. Now if you want to write down the units, so this is going to be momentum is kilogram meter per second, and then divide this by unit of time, which is second. This can be written as kilogram meter per second square. How? Because this is being divided, so it can be brought there. So this is the SI base unit for force. Now here, if we make a momentum as a subject, momentum equals to force multiplied by change in time. If you write the SI units, this is going to be Newton seconds. Remember, the other unit for momentum was Newton seconds. It came from this equation, Newton seconds. Now, according to this, we can also define that force is basically the rate of change of momentum, right? As you can see here in this equation. Now, what if we're talking, okay, let's do an example first. So if you can, try to do this on your own first, and then let's do it together. So a golf ball of mass 45 gram is put along a level green with initial velocity of 4 meters per second. It decelerates at a constant rate and comes to rest after 3 seconds. Calculate frictional force on the ball. Okay, so this is the ball. This is put along right side, for example, and the frictional force is acting on the opposite direction. You're supposed to calculate the force. Remember, we can use this formula. Force equals change in momentum over time. Change in momentum is going to be final minus initial momentum, which is mass into final velocity minus initial velocity. Finally, it comes to a rest, right? Comes to rest, so it's 0 minus 45 over 1000, convert grams into kilograms, multiplied by 4, which is the initial velocity, and this is negative 0.18 Newton seconds. Another unit for momentum is also Newton seconds, and you can simply find the force now by dividing this by time, and this is negative 0.06 Newton. Now, what if a mass is constant? For example, when this is how it is for the most cases, if a resultant force is applied on an object and the mass does not change, what happens? Okay, so let's keep our equation same equation. Force equals to change in momentum over change in time. Remember the formula for change in momentum: mv final momentum minus initial momentum, mu, divided by change in time. Now, since mass is constant, both of them have same values. We can take mass outside, and then v minus u divided by t. If you remember, this is the formula for acceleration. Okay, so F equals to ma. This is a very important equation, and it's very useful. Force equals to mass multiplied by acceleration. Now, this says that acceleration and mass are inversely proportional. If acceleration reduces, mass increases. That means for a given amount of force, if the mass is huge, the acceleration will be small. Or for a given amount of force, if the mass is very small, it will accelerate a lot. Consider that you have a very big and heavy steel ball compared to a light plastic ball. Okay, so if you kick both of them, of course the ball that's light plastic ball will go much further along. It will have a greater acceleration compared to a big heavy ball which has a lot of mass. It will not have a great value for acceleration. Also, it's important to notice that the direction of resultant force and acceleration is same. If the direction is towards right of the resultant force, it will accelerate towards right as well. Now we can also say, based on this equation, that 1 Newton is defined as the force which will give 1 kilogram mass and acceleration of 1 meter per second in the direction of force. F equals to ma. So 1 kg multiplied by 1 meter per second square. This is going to be 1 kilogram meter per second square. So this is basically the SI base unit for force, which equals to 1 newtons. So now Newton's second law can also be stated as for an object of constant mass. Okay, now we need to make sure that the mass is constant. So when the mass is constant, the acceleration is directly proportional to the resultant force applied to it, which is given by this formula. Now let's look at this example. Can you try to do this first? A car of mass 1.2 tons accelerates from 5 to 30 meters per second in 7.5 seconds. Calculate accelerating force on the car. The formula is F equals to ma. So first of all, find the acceleration, which is final velocity minus initial velocity over time, is 3.3 meters per second square. multiply mass by 1000 to convert it into kilograms, and then find the force in newtons. Can you calculate the momentum when it's traveling at 30 meters per second? The formula for momentum is mass times velocity, so it's going to be 1200 multiplied by 30, and this is your answer. You can also write this in scientific form: 3.6 multiplied by 123 multiplied by 10 power 4 kilogram meter per second. Make sure that your significant figures also matches that of question. We'll say this is 5.0, so all of them have two significant figures, and your answer should have two significant figures as well. Now let's move on to the Newton's third law. This states that if an object A exerts a force on object B, for example, if you are exerting a force on the wall, your object A exerting the force on object B, then object B, the wall, will exert a force on object A with equal magnitude but opposite direction. For example, if you are pushing the wall by applying the force of 1 Newton, the wall is also applying same force of 1 Newton. Now this can also be applied to while you're sitting on a chair. You're sitting down, you have a weight, for example, of 100 newtons. The chair is applying an equal but opposite force of 100 newtons. If you're sitting, now this is easier to imagine on a chair, but what about Earth? If your weight is 100 newton going upwards, the Earth does not applies a force of like as much depending on its mass, okay? It applies an equal and opposite force. So if you are applying 100 newton on Earth, the Earth is also applying or exerting a force on you of 100 newtons. Also is happening between magnets. The magnetic force, equal and opposite. Same for between two protons, equal and opposite, and they're being repelled from each other. Now it's very important to notice that these are two objects, okay? One object exerts force on another object, and the other object exerts force on you. Now it's also important to notice that the force pairs mentioned in Newton's third law are not only have the same magnitude, but they're also of the same type. So in this example, we're considering gravitational forces in this one as well. Now we're considering magnetic forces, okay, and electrical forces. We can't compare like gravitational force and electrical force, for example. The force pair are of the same type as well. Now if you look at this question, can you identify the direction of the moon's acceleration? You can see the moon is exerting a force towards the earth, so the acceleration is also towards the earth. Remember, based on this formula, F equals to ma, both of them, acceleration and resultant force, are in the same direction. Now what if there's a ball and you're throwing this ball upwards? Okay, if you throw a ball upwards, what is the direction of ball's acceleration? You may think it's upwards because it is moving up, but what about the force acting on it? The force acting on it is the weight, right? Because of the Earth's gravity. Since it is down, it's also accelerating downwards. Now Newton's third law can also be described in terms of momentum. It says that the rate of change of momentum due to force on one object is equal to the rate of change of momentum due to the force on the other object. So if you look at this equation, force equals to change in momentum over time. Change in momentum is same. Equal force is applied for same amount of time. Basically, when two objects exert forces on each other, their changes in momentum are equal and opposite, okay? Now let's apply Newton's laws. Okay, so there is this object. You have an object which is resting. If it's resting, according to Newton's first law, if an object is resting, it has no resultant force. There is no external force applied to it. So the forces here must be balanced. Now we know that if an object is resting, it has the weight which is acting downwards. Now this suggests that there must be an equal and opposite force that is acting on this book. So this is called as R. Now R represents normal contact force. Basically, any object which is in contact with another object has a contact force, and normal because it acts at 90 degrees or perpendicularly to the plane of contact, which is between the book and this table or surface. Now this book is resting because the value of weight equals to the value of R. Now it's very easy to confuse this with Newton's third law. They may think that okay, these forces are equal and opposite to each other, but it's important that it's two objects that are exerting forces on each other when you're considering Newton's third law. So if the table is exerting a force on the book, the book is also exerting an equal and opposite force on the table. So if you call one of them is R, from the table to the book, normal contact force, there is an equal and opposite a normal contact force by the book on the table. So this is the force pair that Newton's third law explains. Now you might wonder, what about the weight? If there is a weight acting down, there is also an other force acting upwards. That is true basically in physics. Since the earth is attracting the book, basically the book is also attracting the earth. It can be so that's how the forces are balanced. But when you're generally drawing a diagram, for example something like this, and if you want to do some problem solving and solve some question, this is what you do. You mark the weight, which is down, and the normal contact force, which is up. And this is how you solve different problems, by drawing something called as a free body diagram. You draw a rough diagram and draw the different forces that are acting on it. When you're drawing them, make sure that the scale of these diagrams roughly represents the magnitude of the forces. If there are multiple forces acting on it, mention them. If there are different angles, mention them as well. That's going to really simplify problem solving, and this one definitely needs a lot of practice to get the hang of it. Now, if the question says that the object is accelerating, that means there is a resultant force that's acting on the object. So the forces will be imbalanced. For example, if this is 80 Newton, the other one is going to be 20 Newton, for example, in the opposite direction. Okay, now but if there is no acceleration and the object is moving at constant velocity, that means the forces must be balanced. So the resultant force is 0. This one will also be 80 newtons. And now the object is at either at rest or at constant velocity. Now what if the forces are at an angle? You have to resolve the forces. For example, if this is 80 Newton and this is 30 Newton and you need to find the resultant force, first of all you need to find this angle. Maybe it's given to you, maybe it's 20. So you need to resolve the force into the horizontal component, find the horizontal component of the force, whatever that. This is going to be 80 cosine 20. Now if you don't know how to resolve forces, I explained that in the previous video as well. It's very easy. If you want to, if you know the angle, if you already know the angle between the force given and the x, for example, in this case, because we are trying to find x, if you know it, you write cosine. But for example, if you're trying to find the y component and you don't know this angle, in that case you use sine. Now the trick to remember is that you have to stay away from sins. So since the angle is away, you have to use sine if you want to resolve it vertically. Otherwise you use cosine 20. Now let's look at this example. So this question says that try to do it on your own too if you can. This question says that a box of mass 5 kg is pulled along a horizontal floor by a force P of 25 newtons applied at an angle of 20 degrees to the horizontal. So you can see that this is the box. It's pulled by a force known as P, which is at 20 degrees. The value for P is 25 newtons. Let me mention that here. Now, frictional force F of 20 newton is also acting parallel to the floor, which is here. This is 20 newtons. They are asking you to calculate acceleration of the box. Now if you look at the upward and downward forces, the vertical forces are balanced. Weight, the value of weight equals to the R, the normal contact force. So if you draw a diagram, this would be something like this. This is 20 newton towards right, and the object is pulled at 25 newton, an angle of 20. Now you have to basically resolve this force like this, okay, horizontally, something like this. If this is 20 newtons, what is the force in x direction? So this is simply 25 cosine 20, which is 23.5 newton. Now to find the okay, they're asking you to find the acceleration. So the remember, force equals to mass multiplied by acceleration. Acceleration is going to be resultant force divided by mass. What is the resultant force? You have to subtract both of them because they're in opposite direction, right? So this is going to be 23.5 minus 20 divided by the mass. The mass is 5 kilograms, so divide this by 5, and the answer is going to be 0.770 meter per second. Two significant figures. Square. This is your value. Alright, now we'll look at non-uniform motion. Basically, what happens as objects fall through air and what happens as objects fall through liquids. So, what we have studied is that what we know is that if there's an object that's falling down, what is the force that's acting on it? Now, you know that the value for G is 9.81 meter per second square. So, this is the acceleration at which the object is falling down. What's the force that's acting on it? The only force that's acting on it is its weight. So the resultant force equals to the weight, which is, let's say the weight was 10 newtons, okay? So the resultant force is acting downwards and it is 10 newton. What is the value of acceleration? The same as G, gravitational field strength, 9.8 meter per second square. Now you would imagine that this object will continue falling with the same acceleration, right? But that's not correct. What happens is that after some time, the value of weight is there. Weight remains same, right? It's 10 newton. But another force acts on it, which is known as air resistance, okay? I'll call this air resistance here. Now, can you imagine what happens to the resultant force now? This is weight. This weight remains same. Weight is 10 newton. Let's say this air resistance has a value of 2 newton. So, what is the value of resultant force now? This is going to be W minus air resistance. So this is going to be 10 minus 2 newton, which is 8 newton. So you can see that the resultant force has reduced. Now force equals to ma, so force is directly proportional to acceleration. Now the value of acceleration is less than G, less than 9.81. Now after some time, something interesting happens. This is 10, the weight is same, weight is 10 newton, it remains same, but the value of air resistance increases so much, this AR is air resistance, that it equals to the weight. So now what is the resultant force? Resultant force is weight minus AR. Resultant force becomes 0 newton. So what is the value of acceleration? It reduces even further. Acceleration becomes 0 newton as well. Now when acceleration is 0, that means the object is falling down with constant velocity. This velocity is known as a terminal velocity. So the object is falling down now with terminal velocity. Now there are different factors that can affect the air resistance. It depends on the shape of the object. If an object has high surface area, it has higher air resistance. Remember, the value of air resistance will never be more than the downward force, than the weight, okay? Because if it is greater, then the object will start moving upwards, and that is not possible. Air resistance will be much bigger, but it won't be more than the weight of the object. Now what about streamline and non-streamline object? A streamline object has lower air resistance. It takes a greater time to reach terminal velocity compared to a non-streamline object. Now what about speed of object? If the speed at which the object is falling is greater, the air resistance would be greater as well. Okay, so these are the graphs of falling object. We have a tennis ball and a shuttlecock, which are falling under gravity. This is a speed time graph. If you notice, shuttlecock has a bigger surface area compared to a tennis ball, so this has more air resistance acting on it. Now if you notice, initially both of them are falling with the same value of acceleration, which is the same as G, 9.81 meter per second square. Initially they're both same, but after some time the air resistance has started to act on it. The value of air resistance has started to increase, but it's not so much. It is still accelerating, okay? But the value of acceleration is reducing, and then it reduces all the way until where air resistance equals to the weight of the object. So downward and upward force is balanced, and the resultant force becomes 0. That means the object is not accelerating anymore and is moving with the constant velocity of terminal velocity. This is the value that can be taken from here. Now for the shuttlecock, the value of terminal velocity is much smaller. The initial value of acceleration, it reduces until acceleration becomes 0 here. Now, we know that frictional forces are basically forces which act in direction opposite to the motion of object. They oppose the movement of an object. Now, for air, This is known as air resistance, right? So in air, we can say an air resistance. But a more general term for that is viscous or drag force. This is the frictional force that acts in fluids. Now, fluids involve both air as well as liquid. Frictional force is very low for fluids with low viscosity, such as water. If there's water, the frictional force will be lower. But for example, if you have a viscous fluid, for example, wax or honey, the viscous and drag force will be much greater. Now let's look at this example. This is an object is falling in liquid. Now we have said that this ball is falling at a constant speed in oil. So can you draw the forces? We'll also introduce a new force here. So first of all, of course, is the weight of the object, the weight which is acting downwards. Now, there is also an upward force. If this was air, it would be air resistance, but this is a fluid, so we will call this a viscous force. When an object is immersed in a liquid, it also experiences an upward force because of the pressure of the fluid. This is known as an upthrust. Okay, so viscous force plus upthrust. It's important to know this. Upthrust is because of pressure of fluid. This is acting upwards. This upthrust depends on the density of the fluid. If the fluid is very dense, it will have a greater value for upthrust. And there's another name for upthrust, which is known as buoyancy force. You might be thinking, why don't we have this upthrust in air? Why do we only consider air resistance? This is because upthrust depends on the fluid's density. The density of air is very low, so upthrust is negligible. But in fluids, for example, oil, glycerin, the upthrust is not negligible, and you need to consider this. This is falling at constant speed. That means the upward and downward forces are balanced. So W equals to viscous force plus upthrust. Okay, what is the value for resultant force? If they ask you to find out the value for resultant force, this is going to be 0. Because find resultant force, you have to subtract the forces that are acting in opposite direction. Let's say if this was 20 Newton, upward is also 20 Newton, so this is going to be 0 newtons. Now, okay, let's say if the object is accelerating downwards. Can you say which force is going to be greater, downward or upward? It's going to be downward force. If it's accelerating downwards, weight is going to be more than viscous force plus upthrust. Just like when objects are falling in air, this constant speed is also known as terminal velocity. Now we'll talk about something important, which is the principle of conservation of momentum. What does this mean? This law basically states that the total momentum of a closed system. What is a closed system? A closed system means that there are no external forces that are acting on the system. Total momentum of a closed system is same before and after a collision or interaction. That means the momentum before a collision equals to the momentum after a collision. Now, if you look at this example, you have two balls. Ball A is 2 kg, ball B is 3 kg. A is moving towards right with a velocity of 3.8 meter per second, and B is moving towards left with a velocity of 4 meter per second. Now, after the collision happens and after collision, both of them are moving together towards right. What is the final velocity? So according to the principle of conservation of momentum, momentum before equals to momentum after. So if we have to write down this equation, remember the formula for momentum equals to mass multiplied by velocity. So mass of A multiplied by U. What is U? U is the initial velocity multiplied by initial velocity of A plus mass of B multiplied by initial velocity of B. You have two balls, so that's why we're adding them. What about after? Both of them are joined together, so we'll combine the masses and the velocity. It's m of AB and velocity of AB. So what is mass? It's 2 multiplied by 3.8 plus 3 multiplied by negative 4. Now why are we writing negative? Because this is towards left. So in this question, when you have two directions, you have to establish which side is positive and which side is negative. So we'll consider that all the velocities towards right are positive and anything towards left is considered negative. So this is why we write negative 4. This equals to 5v. Why 5? Because this is 2 kilogram plus 3 kilogram equals to 5 kilogram multiplied by v. So now you have to solve for this, and then your velocity is negative 0.8 meter per second. Now, what is the meaning of negative? As we stated, that negative represents left. So this is moving towards left with a velocity of 0.88 meter per second. So now we studied about linear momentum, but we have just studied head-on collision. That means they are in one direction. Sometimes collision also happens in two dimensions. That means that there is an angle between them. So you need to resolve the velocities to make them in one angle. Now, just as a revision, for example, if this is your velocity f moving diagonally, the angle is given as 30. So can you resolve f into y? What is the y component of force? This is going to be f sine 30. Y sine, because the trick is stay away from, since the angle is away from you, you don't know this angle here, so you're going to use sine. What about the horizontal component? This is f cosine 30. Now let's look at an example of collision in two dimensions. So object A is moving towards right with an initial velocity of u. B is stationary, it does not have a velocity. So after the collision, A is moving towards a right with at an angle theta to the original velocity, and B is moving towards right as well, but downwards with an angle. Let's call this angle alpha. Now let's write down the equations for this. So we can either solve this in x direction, which is parallel to the velocity, or we can find it in the y direction, which is perpendicular. It's your choice, but choose one. What is the initial momentum? Momentum before collision is going to be m, mass of A, multiplied by the initial velocity of A, plus 0, because the momentum of B is 0, mass multiplied by 0. What about after collision? So we have mass of A multiplied by velocity cos theta, because we have to resolve this in x direction, okay, plus mass of B multiplied by the velocity and the cos alpha, because you have to resolve this in the x direction as well. And then you can equate both of them to solve for the unknown value, okay. Now what about y direction? So this is only moving in x direction. The momentum in y is 0. It's not moving vertically at all, not even at an angle, so this is 0. What about after collision? This is going to be MAV sine theta, because you have to resolve this vertically after, and then you have to subtract it with MBV sine alpha. Now why are we subtracting it? Because now the velocity is downwards. So when we're considering a y direction, upwards velocity is considered positive, downward velocity is considered negative. That's why it's negative sine alpha. Now let's have a look at this example. A particle moved towards a stationary particle of equal mass with a velocity of 2 meters per second. So particle A is moving towards another particle with a velocity of 2 meters per second. After the collision, one particle moves off with a velocity of 1 meter per second and an angle of 60 to the original velocity. The second particle moves off with a velocity of 1.73 meter per second. Calculate the angle second particle makes with the original velocity. Try to do this on your own. If you are done, or if you're unable to do so, let's do this together. So this is a drawing, a sketch. Particle A is moving towards right with an initial velocity of 2 meters per second. Afterwards, after collision, A is moving towards right with an angle of 60 degrees. What about B? You don't know this angle, you have to find it. So let's write down our equations. I'm writing it in the x direction, but you can write it in either one. So this is going to be mass. Now all of these mass are same, okay, because they all have same mass. So I'm not writing MAMB. That's going to simplify our answer. So it's going to be mass multiplied by the velocity of A plus 0, because the momentum of V is 0. This equals to mass multiplied by velocity of A cos 60, because you have to resolve it in the x direction like this, plus MVB cosine theta. Okay, now we don't know the value of m, so we can't plug it in. Let's take m outside. Let's factor m outside, because both of these values are same. So I just took m out here, and this m is here. We can cancel both of these m, because this is being multiplied as well. You see here, if I was going to bring this m here, this is how it would be. It would be in the denominator, and I can cancel it. So I'm only left with UA, initial velocity of A. Let's plug in the values. This was 2. equals to 1 cosine 60 plus 1.73 cosine theta. I have to make theta as the subject. The angle is going to be 30 degrees. Now we'll talk about another important quantity known as impulse. Remember, force is rate of change of momentum. If we make a change of momentum as a subject, we're left with force multiplied by change in time. This quantity is known as impulse. The SI unit for impulse is Newton second. Okay, so you can say impulse equals to force multiplied by change in time, which also equals to change in momentum. Now this impulse is important when you want to find the force that acts over a very short period of time, for example in a collision. The impulse of force is equal to change of momentum. Now when objects interact or collide with each other, there are basically two types of collisions. The first is elastic collision and the second one is inelastic collision. Let's look at the differences between both of them. So momentum is conserved in both of them, even in elastic collision, according to the principle of conservation of momentum. Okay, momentum before equals to momentum after. But what about kinetic energy? The thing is that in elastic collision, kinetic energy is conserved. In inelastic collision, the kinetic energy is not conserved. So let's look at this example. You have two objects approaching each other, and then after collision, they are moving away from each other. We say that kinetic energy before equals to kinetic energy after. So this is going to be half ma ua plus half mb ub equals to half ma. Now it's a va. Why v? Because this is a v stands for final velocity, plus half mbvb. Now if you're wondering why did I not include the negative signs here, because these are moving in different directions, this is because this is energy, and energy is a scalar quantity, so we don't need to think of the let's simplify this. So here all of these objects have the same mass, so we can cancel out the masses in all of them. We can also cancel out half. Now mathematically, if you want to solve this mathematically, you have to take half m outside, and then ua plus ub equals to half m va plus vb. Now why was I able to take m outside even though this is ma and mb? Because they are same. That's why I took m outside, and I wrote this generally. You can actually remove this to make this even more clear, that this is just m. Okay, I hope that's clear. Now we can cancel out m, so we can say ua plus ub equals to va plus vb. So this leads us to our third point, which states that the relative speed of approach, the speed at which both of these objects are approaching each other, equals to the relative speed of separation, the speed at which they are separating from each other. Now this is only for elastic collision. This does not hold true for inelastic collision. Let's look at some examples. Here two objects are approaching each other with these velocities. You're supposed to find the velocity of object B. So to do that, you can write u1 plus u2 equals to v1 plus v2. So u1 plus u2 is going to be 20 plus 0 equals to 5 plus v2. So this is going to be 15. So this is 15 meter per second. Now in this example, these are two objects. They're both moving towards right, and you have to find out if this speed is correct. Now the thing is with relative speed of approach is, yes, it's also applicable when objects have different masses. Okay, when both of these objects are moving in the same direction, you have to subtract it. All right, so this is going to be 4 minus 1 equals to x minus 2. 4 minus 1 equals to x minus 2. So x is going to be 3 plus 2, which equals to 5. So this is 5 meter per second. That is correct. Remember, you cannot use this formula if the collision is inelastic. Only the kinetic energy is not conserved. Why? Because when two objects are colliding with each other, some of this energy is lost as either heat energy or sound energy, and not all of this energy is conserved. This elastic collision is most commonly observed when collision occurs on microscopic levels, for example, between atoms. And that's all about dynamics.